Yeah, thanks for the introduction. And it's, as already said, a great pleasure to talk today. And I think I would like to relate to what we have heard, heard yesterday, what we will maybe, what we have heard today in particular. So, because we heard already the term self-driving networks and data-driven networks. I have to say, self-driving networks, it's not about cars. It was actually 2 years back when I was attending this workshop organized by Jennifer Rexford and Nick Feamster about self-driving networks. There was also Jeff McGould from Google. When we said it's about self-driving cars and self-driving networks, you run crazy. Because if you think about this, think about your network. Like, is your network driving around? It's not really driving around. Do you have multiple networks that can collide? It's not really about this. So you have to be a little bit, have to pay attention to this, to using this term about self-driving cars or networks. In particular, there's also like data-driven networks. And then people said like, I think our networks, they are already data-driven, of course. I mean, take TCP. It's going through states. States are triggered by data that the client and the sender that they received. So it's data-driven, clearly. So there's the vision. And maybe another question, do you know this car on the left side? So when we get back to what we had yesterday, if you know this car, you know Knight Rider, and then you can be maybe older than 30, 35 years. That's why I decided to put also something on the right side, because I'm struggling with my PhD students when I show this car. They don't know it, so I had to take a movie picture. They know, and they saw in the youth, it's like WALL-E. So self-driving networks is about like networks that measure, analyze, and control themselves. So in the end, we have the human as maybe an operator taking the popcorns, sitting out at the loop, and just watching the network how it operates. And what we would like to have really in the future is like the ability to detect problems. How can we actually say that there is a problem in our network? How can we teach a network that the network knows this is a problem without looking at the data? And then even, which is going to what Ted yesterday said in his keynote, is like that you even equip the network with abilities to solve problems. And this is going to an AI that is maybe rewriting code on your entities, on your network elements. And as a third part, you still have to verify the solutions. So in this case, the network has to know, okay, there was a problem, I'm now rewriting the code, how can I actually verify that what I have done is correct and true? And the more important is that there's a specific problem inherent to this overall self-driving stuff and applying machine learning and artificial intelligence, because we know that data-driven systems, they can be tricked. This is what people are now aware in the machine learning community. I think we also saw this about generative adversarial networks. It's like the third buzzword. That's also what I learned yesterday. It's so important that you have like two entities competing with each other. And then the problem there is if you have one entity like on the left side, where you say, okay, now you're confident this is a panda. For a human, this is quite easy. You can easily add noise that you get a neural network to say with 99% confidence that this is a gibbon. And funny-wise, the same is true in networking. I refer here to a work that Laurent has published last year on ACM hotnets. It's like self-driving under the influence, which is also going this direction to say, our networks, we equip them with machine learning, we have them data-driven. There's a problem. As soon as we put something in that relies on data, if we put in some other data that is like adversarial, we can actually trick our machine learning algorithms. We can actually trick maybe our artificial intelligence. So let's go to this picture. That means there can be an evil guy who knows the insights of your algorithms, who knows how like your machine learning algorithms working, how your AI is working, and he can like then tweak the input to your network that is actually steering to the network to wrong decisions, bad decisions. Really can harm your network. But the point here is that this is not only true for machine learning based networks, for data driven networks. This is already true. I mean, this is already what we see. Take any network designed by a human, take a DDoS attack, it can be attacked. So every kid that is going to a forum can download a script that is triggering some kind of DDoS attacks and can attack your network. And it's getting into states where actually network is breaking. We are struggling in implementing solutions that can help us, or that can, let's say, that we circumvent this, that we can protect against these problems. So adversarial input is not only critical for self-driving networks in the future, it's already a problem what we have. And the question is actually also why. And there I'm referring to the general way how we actually quantify our solutions to the problems we discover. I mean, you have to think about this. Think about your papers you have done maybe in the past when you did research. So the data you took to evaluate your algorithms. There are like two choices. You can either say, I'm doing an algorithm, I'm a theory guy, I have an approximation. You have an approximation guarantee, it holds. You can prove this. But if not, you can just verify empirically, simulations, measurements, and so on. So you have some input, traces, models, or even humans' best guesses. Traces, sorry to say that, but I mean, Google, Facebook, telecom provider, operators, they're not always making the traces available. So it's quite hard for us to verify our solutions to say this is now working for this trace or not. First problem. So then we go to models. If you take, for instance, a PMF or a PDF, so probability distribution function, if you take this data out of a time series, what are you losing? You're losing the time aspect. When you're losing the time aspect, there can be a problem that some states in your network are triggered over time. That means packets, how they are sent over time, can impact your operation in your network. Now you're sampling from, for instance, from a PDF. You're not prepared for such situations in the future anymore. So it's not generalizing at all. So this is a problem about data. Even if we take a trace, say this is the data at the moment, sorry to say that, that's the data of the past. It's not the data of the future, maybe. Next point, human best guesses. So really go to the papers you find in many research projects. They say, oh, let's take this distribution of the packets between 10 to 2000 distributed uniformly and check what our network is about and our performance, and then it's running well. I would even say there are people that are designing evaluations in a way that their algorithms look shiny. It's a little bit offensive, but I think this is possible. So what we thought about is like just as an alternative, that you say, take a data-driven approach. Take the machine to help you on that, to explore like the input, to explore the challenging input. So can the machine be the alternative opponent in our case? So it's something like you can really use machine learning, artificial intelligence for testing, verifying maybe your solutions. So the point is then not only that there is adversarial input in our networks, or that there is adversarial input that can harm our solutions. It's about how to find this input in an automated way that we can say, this is really benchmarking our legacy networks as well as our self-driving networks. So what we know is the traditional way. We have like in the middle, we have the problem instance, routing problem. We have to route from A to B. We have a network algorithm, which is like Dijkstra and so on. We have then a solution, which is like the route. In order to verify our solutions, what we are normally doing, we are creating a lot of problems in simulations. We are creating a lot of problems, maybe measurements and so on, traditional way. A lot of people are now saying, yeah, let's take machine learning. That's what we have seen the whole morning until now to improve our solutions. Put machine learning in, put AI in, it can help us. That's what we have done also over the last 3 years. But what we wanted to do also is like to have something besides. For instance, do you know, or how would you define intelligence? How would you put intelligence into a math formula that you can say in the end, what your network is doing is something intelligent? Are we going to do IQ tests for networks in the future? I don't know how this works, but there are some interesting approaches like empowerment. So if you would like to read about this, check this out. Empowering your networks, what does it mean? It's actually a way to not optimize for objective anymore, but to let the network do something that makes somehow sense, that is for as a human that you prepare maybe for the future, even if you don't know what is coming up. So that's why, for me, the interesting part is the left side now. This is what I would like to focus a little bit on. So what we have done are just like 2 minor publications so far, SICOM workshop paper and student workshop paper, which is about taking the machine to drive how the problem instances, how the data is actually generated to benchmark to verify your solutions. And the end, what we're ending up with is like this approach of saying we have machine learning and AI on the left side. This is now our other opponent versus us as a human in combination maybe with machine learning and AI to really bulletproof our networks, make them bulletproof. And what is it also about? To make it, in this talk, fast and efficient. I mean, it's not just about finding adversarial inputs. That's the point. I mean, you can look maybe into the code if the code is available. You can say, okay, if they put this in, then maybe it will break. This is what fuzzing is actually doing. So this is also what is related here. But that's not about that. It's about like how to make this fast and efficient. And what I would like to present are these 2 papers. So NetBore on the left side and ToxinNet is on the right side for the particular use case of data centers. Actually, data centers are, as we know, very important. They will consume a lot of energy and so on. So it's a quite important research field also in the ASM community and so on. And if you, for instance, running machine learning applications, they're running normally in virtual machines, of course, and these virtual machines are hosted on something. This is like the server. On the server, in order to connect your virtual machines, there is a software tool in most cases in the hypervisor. So when you download this, the open source version, like if you download Proxmox, Xen, whatever you use to virtualize, or you make kernel-based virtualization, you need an entity that is behaving like a switch, which is in this case the Open vSwitch. Why is this piece of software so important? Somebody would say, yeah, this is just a piece of software. Just to mention it, it was first developed by Nicira, which was bought in 2012 by more than $1 billion by VMware. So if you would have been one of the founders of this company, I would say the money problem in your life would have been solved. So it's a quite important piece of software. But of course, we are benchmarking the open source variant here only. So what we are doing is like, for this particular case, we really wanted to go to a test bed. We wanted to have something real where we see really data on the network. That means, to make it simple again, you have a host, a server, you have virtual machines on the server, and in order to interconnect them, what you have on the server is like a traffic generator and traffic sink. In order to interconnect them, you have the Open vSwitch, for instance. And what we wanted to ask ourselves, okay, the traffic generator that is sending traffic through this Open vSwitch, there's a kind of configuration, how we send our traffic over time. That means it's creating then, based on the configuration, packets over time. You have the number of packets you're sending over time on a regular basis. You have the interval time between these packets you're sending over time. And then what you have is also a simple setup of this Open vSwitch. And in this case, we just say, we want to forward only the green packets, for instance. So there's a rule, forward just the green packets, and the rest you should drop. Quite simple. This is a kind of a state you have in. And if you know a little bit more about switches, then there is a kind of growing matching table to make them fast and efficient. You have to clean up this matching table over time, and this is impacting the performance. So the goal in this case is then to find a network configuration that, in our case, because we wanted to find weak spots, is actually maximizing our CPU load. And this is, of course, is challenging. I mean, if you think about the whole configuration space you have for network packets, it's already tremendous. If you're not looking only at the bits, if you think about the packet header length, if it's like 40, 80, whatever for IP, TCP, and so on, then you have 2 to the power of 80 possible combinations of packets. So the human is here still involved. So the human can say, for instance, it makes sense to have a kind of distribution of the packets. So this is where I'm limiting now again myself a little bit. You can put, for instance, different protocols in, like VLAN. You can put different VLAN fields in. As said, you can say, should we send 1 to 5,000 distinct network packets? What's happening? How should we send the packets, maybe in batches or not, over time? This can all be influenced by the configuration of your traffic. So this is what we are taking. Again, back to this picture. Traffic generator on the left, traffic sink on the right, Open vSwitch in the middle. And now what is the problem? If you put the Open vSwitch on any server with any kind of operating system around, the performance might depend on these settings, on the libraries you have around that. That means, in the beginning, if you cannot model it completely, you know nothing about the performance model. You don't know how the performance will behave in this system. And this is also a critical point. I mean, how can you're buying stuff you don't know the performance about. How do you know how many of these things you actually need to buy in order to set up properly your circumstances? So you need to know somehow, get some insights. So you're interested in having this performance model. And this is where we're using this kind of Bayesian optimization approach. So what we're doing really is just, I have to say honestly, we just take Bayesian optimization. It has some tweaks and some how to say, some knobs you can tune, which is like the acquisition function and the posterior stuff and so on. Anyways, we use this to explore this configuration space. That means we use Bayesian optimization to set the configuration. Our configuration in this case is 2D, is the interarrival time and the number of packets. So this is what we can tweak. We can say, for instance, set the interarrival time to 3 milliseconds and send only 5,000 packets. Then we measure until confidence reached. This is like where we need some kind of engineering task. We have to create a measurement loop. This is running over time, and we have to run as long as we are confident the CPU for this configuration point is really like 20, 30%. Then we are getting a measurement point, and then we are updating our model. This is what you're doing with Bayesian optimization. So if you had some random samplings, your model looks like this. There's just one measurement point, and there's like a kind of belief that the performance of this overall Open vSwitch looks like this, that in the middle of the interarrival time, and there's maybe the highest spot of CPU utilization. And then what you're doing is like, based on this, you're guiding the search. So you're going to the next point. This is what you now see. and then you're somehow going to the next point with the crosses over there, and then you're going to the next point, and then to the next point, and to the next point. And in this time, you have, of course, changed the traffic until actually you reach a point where you have a CPU utilization of 30%. And the other configuration points, the CPU utilization is only 0% or 0 to 1%. Okay, why is this now so important? So what we have here, for instance, is the CPU performance model of the Open vSwitch for the interarrival times and the number of packets. These are all both configuration parameters, nothing else. And it looks like a moon, and it's a non-trivial model. It's a performance model that cannot be easily explored. This is the point. And the netboard, actually with Bayesian optimization, what we actually were able to show is that we found this spot automatically. And now what is important, what is interesting about this measurement point here. So if you follow me with the crosses, there is a cross up left with 5,000 network packets and 1 millisecond interarrival time. And there's another kind of cross where you have 4,000 network packets and an arrival time of roughly 3 milliseconds. So the left up cross, you're sending definitely 3 times less, more than 3 times less network traffic. But your CPU is differing by 20%. So there's a kind of configuration where you're sending actually less network traffic, which is counterintuitive to most of the people maybe, which is triggering a kind of state in your Open vSwitch, or it's a kind of operation in your Open vSwitch where you have this kind of utilization. So surprisingly for us, sending less network packets, we could say, over time can actually lead to significantly higher CPU consumption. The details about this I've put into the abstract, so you can, the backup, you can ask questions or not later. And so let's go to the next use case. The next use case is more from a global perspective, because what you have to do in data centers is you have to route traffic between the servers. That means if you look at the overall links, what is happening, you have to route traffic from like the green one from the left server to the green servers in the middle and so on. And you have to route other flows which are arriving over time as well. That means in the second scenario, what we are looking at is which is like what you see really in data centers, network flows, requests for traffic arriving over time. And your routing algorithm has to take actually decisions. And what we wanted to ask also here as a question is, okay, if we are going to simulate this, so this is now a simulation-based setup, if we're going to simulate this, and if we just randomly create our kind of flows, how they arrive over time, with the source and destination also randomly distributed, with the volumes also randomly distributed, what will be the performance of our algorithm in the end? And the question is, for instance, simply by looking or changing the volume, can we find a configuration that is really challenging for our algorithm? It's like that we want to challenge our algorithm, we want to find a configuration where our algorithm is getting worse in the sense. Flow completion time, why is it so important? Because it's mainly determining the performance of applications in the data center in the cloud. The smaller the flow completion time, the better the performance, the application performance. That's why it's so important. You can formulate this as a kind of optimization problem, but we are looking at the other side. It's not the kind of primal dual. It's like left to the right of the problem. And what we ask is is there a setup where we have then to find these kind of challenging input sets? And that's what we are actually then doing with Toxin. And now how does it look like over time? So what you see here, when you know a little bit about genetic algorithms, actually that's what we use. So Toxin is used in genetic algorithms. What we can see here is how over the number of iterations or generations we are producing, so this is the working behavior, you're permutating populations, how actually this kind of flow completion time is getting worse. And it's getting actually worse by more than 35%. So compared to random load you generated, you can, for instance, with just applying genetic algorithms like this, you can create flows, or you can create flow settings in which the performance of your algorithm is decreasing by 35%. And the problem about this is finding these weak spots is not so easy when you just do, for instance, grid search or whatever. You can miss these points. And why is this happening? So it's also, again, not rocket science. What you see here is the flow volume over time. And what is the difference? So you have the red curve where you see the flow volume over time. The total flow volume is varying around somehow a mean of 250 Mbits. And then the optimized one. And what you see for the optimized one, there's a kind of grouping. So the volume is increasing up to a peak, so where the flows are somehow grouped together. This is at this point here. And this is also what you see when you look really at the flows, how they are distributed over the racks. What you have here, the dots, or again over time, what you have here is the source destination IDs. And what you see are the different volumes. So the yellow ones are the smaller ones, and the black ones are the largest ones. And what you can see in the green area is again that the black flows are put on the same source destination links, and they are like somehow running in parallel. I would not say, of course, this is somehow intuitive. You as a human could have come up with this as well. It's like a logical thinking that it makes sense, put large flows together, put them in parallel. It will lead to high congestion in your data center. But of course, I believe that there are much more challenging or not so easy configurations you might see as a human. So this setting somehow makes sense. This is also where you can verify that it makes sense, and it helps you actually to rethink your implementation of your algorithms, or to think about, okay, what should you do in these situations? How can you actually do something in these situations, and so on. Yeah, this is already bringing me to the end of the talk. Adversarial input can harm your system. I mean, it's not about breaking your system, it's also about harming your system. It's like increasing the utilization of your systems, making them inefficient, making them slow. It's like you still win the competition in a 100-meter race if you just slow down the other guy. You don't have to break his legs, you just have to slow him down. So this is like what you can have fear. So if there are people harming your system, it's actually leading to worse performance, of course. What we had in this talk is like this idea of having a data-driven approach to automatically generate adversarial input. So it's not about knowing and finding adversarial input, it's finding it in an automated way in order to make your systems then bulletproof. A lot of information is, of course, missing. Measurement details, simulation details, details on the used machine learning and artificial intelligence algorithms. Also the future work, the problems, I think there are still many. But what we believe is like that concepts like what we thought about, like netboard, toxin, should be something it's like an integral part in your verification of your solutions when you propose networking solutions. It should be like this, that maybe in the future you just say, yeah, we used our machine learning algorithms and competed with X, Y, Z, not only the data set, but with like the algorithm that is like generating this input over time. These are the references, and that's it. So thank you. And if you have any questions, I can hopefully answer them.
Questions for Andrea?
Thank you. Interesting talk in terms of usage of Bayesian optimization. What's the dependence on your traffic generator? I mean, which distributions do you use for generating traffic?
That's what I said. This is where the human is still involved. So what we had is a setup where we said, for instance, we wanted to have packets where we can set VLAN tags or not, where we can set the source IPs, the destination IPs. So we had a kind of set from which the Bayesian optimization can choose. Criteria were then how different these packets were. So a kind of entropy, you can say, how different they are in your traffic. The interarrival times was important so that we can somehow determine interarrival times between the packets. Also the batches, so how many packets are sent as fast as possible together. I mean, of course, there's an interarrival time, but like going to zero. These were the first things we just used in the preliminary evaluation.
Do you have a statistical analysis about the distribution of what you were generating?
It was all uniformly distributed. So
uniformly?
Yes, this is where we chose from.
Okay.
And then what the Bayesian optimization is actually doing, you have the performance model, and then he's trying to make the configuration point. So this is what we are choosing then. So actually what you're doing is like you're somehow learning which, let's say, mean interarrival time you should choose. This is what you're learning over time.
That was my second question. When this Gaussianity assumption will disappear, and what you might have in certain traffic patterns, what's the likelihood that Bayesian optimization would have a straightforward use as you were showing here? Because I think you were using, you did not yourself develop the Bayesian optimization.
No, of course not. Of course. Yeah.
So the question that is there, and the generalization of Bayesian optimization for non-Gaussian priors actually requires an effort, and do you see this as a valid research, I would say, direction for the future?
Yeah, I mean, definitely. I mean, the point about the Bayesian optimization is first that it depends on, so there are many somehow concepts. I mean, there was even this workshop. The problem with the Bayesian optimization, the traditional one, call it traditional, is for instance that you rely how you fit your model on a Gaussian process. Gaussian process has cubic time. And there is now, if you look into the IMCL community and NIPS and so on, so machine learning community, there are like really papers now talking about Bayesian optimization for Bayesian optimization, or like papers that propose to make the Gaussian process obsolete with a neural network. There's a concept about this from 2019 in order to speed up the overall process. So actually the Achilles of this thing is like the Gaussian process a little bit in the setup. Because if you increase your configuration space, you have the same problem in the end. But you are still, I would say, a little bit faster than just doing crit search or random search or just any guesses or just take one example like a trace, and that's important.
Thank you, Andrea.
Thanks. Great talk.
Thank you.
So when we presented the Hotnets paper, the question, one of the questions we got in the audience was that, but that's not new. I mean, TCP has been driven, as you said, for a while.
Yes.
And so there's been like so many attacks on TCP in the 80s even. And then, of course, there are attacks on BGP. You can inject message in BGP.
Yeah.
We have attacked OSPF in the past. So, okay, we answer something, but I was wondering whether you can share your views on this, whether you see like a fundamental difference, or perhaps it's just that the attack surface now has increased a lot, and that's the key driver. So I don't know if you have thought of this on this particularly.
Actually, yes. I mean, I'm thinking about this a lot because, as you said, this is like the criticism you have to answer. First of all, I think the kind of ability to do something in the network is increasing. So increasing, let's call it flexibility, leads to increasing options. So let's say earlier we had routers which were closed, like you said. Now the routers are open, so we can somehow, like SDN, we can control them. That means it's increasing our options. So I would say the attack surface, of course, is increasing. Like the point about what we have nowadays is like we have this computational power which was increasing, which is actually enabling us to run now really simulations, like what was also mentioned in Nokia talk, that we can say you have in a simulation, you can now make an intensive analysis of some of these effects much more efficient. As long as Moore laws still hold, it will work somehow. If not, of course, the point is then you need some ways to still say you verified your solution. So, and the problem I always also have is like, okay, if you have solutions which can be verified, which means really like people that are doing algorithms with approximation guarantees, they say, as long as I cannot do this, I don't propose any kind of algorithms. But still, we are living in a world where we put like pieces on software, on hardware, into networks, interconnect them, where we have many components. And I think we need ways to that help us to somehow explore this kind of configuration space. Because already, I mean, if you think about TCP, there's this paper of PCC, for instance, also what you mentioned, and we took the algorithm, or I worked with someone who took the algorithm, and he wanted to re-verify the results. And when you look into the paper, funny part is like they verified only the situation when there were flows coming into the system. So he set up a system where the flows were leaving the system, and this machine data-driven algorithm was not getting back the bandwidth. So when it was like sharing fairly the link, it had 50%, and then the other flow was leaving. The model was not trained for this. And this is what you should try to avoid when you're doing these kind of things. It's not new in the sense. And it's also, I mean, what you have also is like fuzzing. Fuzzing is something a little bit similar. When you do program fuzzing, when you do input fuzzing for programs, it's well established in the domain. There's Cloud Fuzzer from Google, for instance, if you know this. This is where they generate input HTML requests for the Chrome browser. Found until now, I think 16,000 bugs in Chrome in this way. What is a little bit different, this is also the point about networking, is that we have the timing issue. So there is no hope, I would say. We have to go to the time domain. We have to analyze actions that are going in over time because we have this kind of states in our network, which makes it then also tough. And this is where we need to find ways and solutions to help us as researcher engineers to discover problems and weak spots.
I guess we don't have time anymore, but so I'm not sure AI is the answer there. So
yes.
So that was perhaps is more like a provocative question here for this audience, right? But if you assume that you have the code, right, there are like techniques to analyze, do static analysis, and here in your example in Open vSwitch, right, it's open source. I can have the code, so I don't really need the AI and kind of like make my work harder because I need to reverse engineer the entire code by kind of like through the input output. So probably there are things to do there, and you can do like. I mean, the static analysis of code would be like one obvious things to look at. And there is also this entire field of complexity analysis on algorithm, right? I give you like a sorting algorithm, and I want to find the worst case input that generates more like steps. So this is also something probably there is inspiration to be taken from.
So for instance, this is also where we took the inspiration from Quicksort. Quicksort, like if you have an algorithm that is where you put in a sorted list, then of course Quicksort is like has polynomial runtime, so square on O and square. But the point is like algorithms. So when you have an algorithm, you have something that is really clear. It's really an algorithm. You know the lines from A to B. But what we have is like we put the algorithm into the system where it has to work together with some other components. For instance, in the Open vSwitch, the problem was not like the Open vSwitch call itself. It's also the problem that the Open vSwitch is using a data structure that is having a C function call, which is very costly. And then the point is also like, how do you know over time? So it's, I would say, quite tough to know somehow a little bit over time that this 10 seconds timeout rule, which was actually leading to this problem, what is seen here on the slide, is leading to the high performance consumption. So there were some developers that just set this timeout to 10 seconds, push the code. And I mean, it's just one piece among 10,000 lines of code or 20,000 lines of code where you just say this is 10 seconds. And this kind of thing is then leading to the problems here. This was for us interesting. I would say it's not so hard to plug in machine learning here. This is the most important part. So Bayesian optimization, for instance, to set it up in this way, if you have a simulator, then it's quite straightforward. Might not take more than 30 minutes for some simulations if your simulation is well programmed.